So first, this reaction converts a vicinal tetrahaloalkane to an alkyne. When I say vicinal, I mean that two of these halo groups, like bromines, for example, are attached to carbons that are adjacent to one another. And in the presence of a strong base, this can produce the alkyne, especially for the second step. This generally proceeds through an EU2-like mechanism. Starting from this molecule, we can see that there are two relatively acidic protons here. I've underlined these here just to show them. So here's the mechanism. We start this reaction with two relatively acidic protons, which I'll show in red. Okay, and then these are going to react with a strong base like sodium amide. Okay, we'll have an excess of that base. Okay, so that sodium amide itself will come in, deprotonate this relatively acidic hydrogen, create a double bond, and then kick out the bromine in a classic E2 mechanism. Okay, and this stereospecific process will lead to this alkene. A second step of sodium amide will deprotonate the other acidic hydrogen, okay, and create this dibrominated alkyne. So it's important to say that this reaction will have an excess of sodium amide and that you're using a base that's at least as strong as sodium amide so it can deprotonate that acidic hydrogen that I've underlined in green or circled in green in this second step. So some questions you can ask in office hour. First, why is a strong base required in this reaction in the first place? Two, are side reactions possible given this kind of reagent? And three, are there less harsh ways to synthesize alkynes? With that, that's been Organic Chemistry in 5 minutes or less. Thanks for tuning in.